All right, functions. Function notation, right? So functions are all around us. We're going to define what a function is. We're going to evaluate functions. We're going to find the domains of functions, and then think about how to represent functions in different ways. So functions are all around us. So for example, we could be thinking about heights and the age of people, right? So the height of a person can be a function of their age. Right? So here we have a graph where we have their ages along the horizontal axes and their heights in the vertical direction. We could have temperature as a function of dates. Could also be times. So like throughout the day, various times, or days of the year, something like this. So we can of course have temperature as a function of the date. And here we have postage prices as of 2014. So the price of mailing something, an object, is dependent on the weight of the object to a certain extent, right? So something weighs between 0 to 1 ounce. This is what they charge, 98 cents. Something weighs between 5 to 6 ounces. I'm sorry, between 4 to 5 ounces, inclusive of 5. They charge $1.82. So postage is a function of weight. Temperature is a function of the date. Height is a function of age. So just different examples of where functions can be used. Okay, so that's just what we just said. Some other examples. The area of a circle is a function of its radius. The number of bacteria in a culture is a function of time. The weight of an astronaut is a function of her elevation. The price of a commodity is a function of the demand for the commodity. The rule that describes how the area of a circle depends on the radius r is given by the formula area equals to pi r squared. Okay, so definition of a function. A function is a rule. To talk about a function, we need to give it a name. So we usually use the letters F, G, H. It's just sort of common, customary results. So for example, we can use the letter F to represent the rule that follows. So F is the rule, square the number or square the input. And we can define that set of instructions of squaring the input or squaring a number by the letter F. We can define it that way so we can reference it. So a function is a rule that assigns to each element x in a set A exactly one element called f of x in a set B. So this let's explore this for a little bit. So we are used to working with something like this, right? Where we consider this as the input and y is the output. So all we're doing is we're going to rewrite this to follow this notation, f of x equals to x squared, where the f of x together is the y. F of x is the y. Okay, so the only thing that I think people have a real difficult time with is distinguishing that the letter f here is not a variable, right? So a very common mistake is people do this. They take the f of x equals x squared, and then they divide both sides by, I don't know, divide this side by x, divide this side by x. So they get that f equals x. And they simplified it this way, and this is nonsense, right? This doesn't make any sense. You have to really understand what the f represents here to recognize that you can't do this. Good. Okay, so f is not a variable to be solved. You cannot add it, subtract it, divide it. F of x together, this little unit thing right here, is the output, it's the y. It's just there's some value. There's a lot of value to writing it this way, as I'm sure this is reviews, so I'm sure many of you guys are already aware of this. But at any rate, okay, so the little unit f of x is the output. It's the y. And it's going to be a rule where the input value x is assigned to one output value f of x. The set from the input values is called the domain, which is typically we use capital letters to represent sets. So often we use set A to be the domain, and set B to be the range. Okay, so the symbol f of x, right, as I've been saying. So this notation reads as f of x, and it's called the value of f at x, or the image of x under f. These last two are not as popular as just saying f of x. The set A is the domain of the function, and the range of f is the set of all possible values of f of x as x varies throughout the domain. So it's all the possible outputs. The domain is all the possible inputs. The f of x is all the possible outputs. The symbol that represents an arbitrary number for the domain of x is called the independent variable. Usually we like to use the letter x as the independent variable, but it doesn't have to be. The symbol that represents a number in the range of f is called the dependent variable. Usually we like to use the letter y, but not always. And in this case, we're saying that the y is also written as f of x. Remember, a little unit thing. You can't separate the f from the x. Good. Then x is the independent variable and y is the dependent variable in the traditional way of writing a function equation and function notation. Many of you guys might have used the machine diagram to describe a function, right? A function is like a machine, the machine f, where we input values of x and the output is f of x as the output. And inside the machine there might be some set of instructions. You know, whatever the input is, double it, add 4, divide by 7, take the square root of the whole thing, right? There's operational instructions that are provided for every qualifying input value, and then after we apply those instructions, we get an output value. Good. And remember, for a function to be valid, there's only one important rule we must remember. A function must be a situation that every time we input a valid qualifying number, every time we input a value, there is a unique output. Right? Now, we are not allowed to have a case where we input one number and out comes different answers. We have to have one unique answer every time we input something. Good? Questions? What we are allowed to do is we are allowed to have different numbers give you the same output. Right? So that little confusion happens. So there could be a case where we input a 3 and then the machine says double it, triple it, multiply by something, divide. There's a set of instructions, and maybe the output after all that work is the number 1. Well, it's also possible that maybe if we input the number 7, for whatever reason, square it, subtract 2, divide, take whatever the instructions are for f, after all that work, maybe it still gives you a 1. And that's okay. That's a function. We're okay with that. What we are not allowed to do is have a case where we input a 3 and we square it, divide it, do whatever we're going to do in here, and the output is a 2, but also the output is a 9. You can't have that for a function. Each input must have a unique output, not 2 different outputs. But we are allowed to have different inputs give you the same output. Any questions about that? Here is a graphical representation of that same thing. We use these little jelly bean style things to describe inputs and outputs and domains. So this would be the domain of the function. And this blue one would be the range. right? And so here we are describing a mapping. If the input is a 1, if the traditionally x, right, if we have f of x style notation, then we're inputting an x value. So here we're saying x equals to 1. Now, we didn't describe the actual operations that are happening. Am I going to add something, divide something, multiply by something? The actual set of instructions was not provided. All we know is that when you input a 1 into your function, the output is a 20. And when you input a 2 into your equation, the output is also 20. That's okay. We're allowed to have that under functions. Different inputs are allowed to have the same output. And here the 3 maps to 30, and then the 4 maps to 40. Good. So if this was, the way it's described, this right here, these numbers are exactly the only values in my domain. My domain is made up of 1, 2, 3, and 4. And my range is made up of exactly 20, 30, and 40. Okay, here's a couple, here's another example. So this is the one we just covered, but here's another example. 1 is being mapped to 10, and then 2 is being mapped to 20, but also 2 is being mapped to 30. That's a problem, right? In a function, you are not allowed to have this case right here. The case where one input leads to 2 different outputs, right, fail. Oh, it says right there. I don't want to bother writing it. It says no function. Okay, a function f is defined by this formula. Okay, so we have this formula, f of x equals to x squared plus 4. Express in words how f acts on the input x to produce the output f of x. Okay, so we can use the language of input. Right, so here is our input value. And we can verbally describe this as saying when you get an input, you want to square the input and add 4. Square input, add 4. And then, English allows you to have some versatility here. You can say add 4. You can flip these around and say add 4 to the input squared. Or you can also say something like 4 more than the input squared. Okay, so you get the point. There are different ways to verbally express this set of rules, that when an input is given, you're going to square it and then add 4 to it. And then this is the output, so you can also throw that into your language. The output equals 4 more than the square of the input, for example, is another way of expressing it. Okay, so we can express it in words. Part B here says to evaluate these. So find f of 3, f of negative 2, f of negative 5. So we have f of x equals to x squared plus 4. And then it says find f of negative 3, 3, negative 2. Okay, so this is saying that I have this like this. And if I want to evaluate this when x is equal to 3, this notation like this means that x equals to 3. And so I replace the 3 over there. Now remember, this is the y, it's the output, so there's nothing to solve here. You don't have to divide by 3 or anything. So from this point forward, we just say that f of 3 equals to 9 plus 4, or f of 3 equals to 13. And this style of notation tells me that the output is 13 when the input is 3. X equals to 3, y equals to 13. Right, so that's the nice thing about this style of notation, that it allows me to preserve what the input was and what the output is, because they're related to each other. Right? The answer is 13 when the input is 3. Good. Okay, well, same thing for the other ones. I'm sure you're very good at evaluating things, so I'm not going to spend more time on that. So evaluating a 3 means we replace the 3. Evaluating a -2 means we replace the x with a -2. We're evaluating at x equals to root 5, we replace it with root 5. And so we end up with these corresponding output values. The domain of the function. So the domain consists of all possible input values for f. So when we're considering the domain of the function, we really have to think about where possible problems can arise, right? And there's only a couple of problems we have to think about. Are we accidentally dividing by 0, right? That's something to consider. And the other thing is, are we accidentally taking the even root of a negative number? And in this case, we have a very simple quadratic equation. That's never going to happen. There's no possible input value of x that would result in me dividing by 0. And there is no input value of x that would result in me taking the even root of a negative number. So there is no problems. There are no input values that would result in an undefined. So the domain is all real numbers. The range, on the other hand, can be a little trickier. You have to think about all possible output values, and that can get a little tricky. All possible output values, well, considering all the possible input values for x, this part by itself is going to definitely be a positive number, right? Anytime you square any value, you're going to get 0 or more. So the smallest this could possibly be is 0 up to infinity. It can get infinitely large, but the smallest it could ever be is 0. And so if the smallest this could ever be is 0 and you add 4, then combine this side over here, the smallest it could ever be is 4, going up to infinity. And so that turns out to be the range. Good. So the range for this one is from 4 to positive infinity. Another way of getting that is to graph it. If we graph this quadratic, we know that it's going to be a quadratic shifted up by 4. Good. So the input values are all possible x values. And as you can see, we can always input a value of x going out from negative infinity to positive infinity. So this is the domain. From negative infinity to positive infinity. On the other hand, the output values, I don't know what would be, how about blue? The output values start here, and they go this way. There's no output value that would ever be a positive 2, or there's no output value that would ever go into the negatives, right? The output of this could never be -5, for instance. And so these values here are the range. And they start at 4, and they go up to positive infinity. Evaluating a function, as we just did, if we're given an equation in function notation, for example, f of x equals to 3x squared plus x minus 5, we can think of the x as the blank. The input value goes there. So we can let x equal to 0, we can let x equal to -5, whatever value we want. We just have to be careful to apply it. It's very easy when we have a number. Like if I said let x equal to 4, okay, so we replace all those blanks there with a 4. But keep in mind that I could also replace it with another letter. I could say find f of w. All right, well that seems silly. All I have to do is let x equal to w, so replace all the x's with a w. Or I could say let x equal to w plus 3. Okay, that means I'd have to replace here this with a w plus 3, replace this with a w plus 3, replace that with a w plus 3, and then simplify it from there. I might have to square this, combine like terms, and all that stuff. We simplify, combine like terms, reduce everything on the right-hand side, but remember that this doesn't get distributed, simplified, or canceled, or anything at all. We'll review some rules later about what you're allowed to do here. But in general, you don't want to treat this like a variable, so you don't distribute the f and cancel and all that, right? We leave it alone because this is saying it's the function evaluated at w plus 3. So here's an example. We have the same equation, f of x equals to 3x squared plus x minus 5. So if we want to find f of negative 2, we just have to replace all those input values with a negative 2. Or if we want to find f of 0, all we have to do is replace those input values with a 0, and so on and so forth. So these are pretty easy. So let's jump to the answer. So this one was f of negative 2, so replace all those x values with a negative 2. And then f of 0, well, that one's really easy. 0, 0, it's just going to give me a negative 5. 0, 0, it's just going to give me a negative 5. And f of 4, replace the x value with a 4. Or f of 1/2, again, replace x with the negative, with a 1/2. So those are really easy, I think, I hope. Notice that the net change in the value of a function f is the value of function f as the input changes from a to b, where a is less than b. So the net change is described by f of b minus f of a. So it's kind of like the change in the y. We have an x-axis here. We have some value b there, and we have some value a there. So the net change in the value of the function as the f in the value of function f as the input changes from a to b is going to be equal to the net change that happens here. So it started off as an f of a here, whatever that answer is there, and it goes up through some value f of b. This is the y-axis. So the net change is going to be this difference here. The domain of a function, when you're asked to find the domain of a function, you're looking for all the set of input values that make the function valid. And so what you really want to do is ask yourself what are the values that make it invalid. And again, like we covered a minute ago, all we have to do is think about the possible input values that would cause you to divide by 0, or all the values that would cause you to take the even root of a negative number. That's really the only two considerations we have to think about. So if we have a case where neither of those things are possible, such as this case here, then the domain would be all real numbers. Good. Unless the domain is specifically given to you. Like in this case, they're saying let the domain be the values from 0 to 5. X is any value greater than or equal to 0, less than or equal to 5. So in this particular example, the domain is set. But if this wasn't given to you, you were just given this and you're asked to find the domain would be all real numbers, because there is no value for which you would be limited by some undefined. Good. Okay, now the range then would then have to be all the possible outputs. So you'd have to consider all the possible outputs that you can get once you restrict the values of x to be any value inside your domain. Usually ranges are just a little trickier. Okay, but for now we're just focusing on finding domains. So if we're looking at an equation like this one and you're asked to find the domain, we have to take into consideration that we might accidentally divide by 0 if we let x equals to 4. So the domain is any number except x equals to 4. We can write that this way. The domain equals to x such that x doesn't equal to 4. Right? Or a lot of people just write all real numbers except 4. That's fine. And then here, remember, we're not allowed to take the even root of a negative number. So as long as x is greater than or equal to 0, then we're okay. So the domain is all numbers that are greater than or equal to 0 in this case. Let's look at these cases real quick. Find the domain of each of these. The domain of the first one, well, clearly I'm doing some sort of a division, so there might be a value that causes me to divide by 0. So what I have to do is pull that off to the side and figure out what this is. What values of x give me a 0 so that I don't divide by 0? Well, this one's easy. We just have to factor out an x. And now we can say by the zero product principle that either that's 0 or x minus 1 is 0 over here. So x equals to 1 there. So there are the two values that would result in a 0 in the denominator. The domain is everything else. The domain is all real numbers except x cannot be 0, x cannot be 1. Those are the only two things we have to avoid. So you can just write it down like this, or you can use this notation of negative infinity up through 0, don't include 0, union with 0 up through 1, union with 1 up through positive infinity. So that's fine. Or the set builder notation, which is squiggly x such that x does not equal 0, x does not equal 1. Right? Any one of those is fine. In here, what we want to do is figure out the values that do not give you a negative inside here. So I want to find x such that 9 minus x squared is greater than or equal to 0. That's what we want to solve. Okay, so add x squared to both sides, and we get x must be this. Or flipping it around here, we have this plus or minus 3. And you're like, wait a minute, what is that? Looks weird, right? Okay, so don't do it this way. We have 9 minus x squared is greater than or equal to 0. We've covered this before. What we want to do is factor this. We have 3 minus x, 3 plus x, greater than or equal to 0. So we have a multiplication of a binomial. Remember, this is a difference of squares. And now we can do the thing where we set up the number lines. Here's a number line for 3 minus x. Here is a number line for 3 plus x. And then we can have a number line for the product of the two. 3 minus x times 3 plus x. Okay, so set up where your zeros are on the number line. And then the 0 that happens here, when x equals to 3, we get a 0. So x equals to 3 is the 0. To the right of that number, when I put in numbers that are bigger than 3, like a 4, a 5, or a 6, I'm going to get a bunch of negatives. And when I put numbers that are to the left of that, I'm going to get a bunch of positives. Plus, 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 including over here. If I let x equal negative 1, for example, 3 minus negative 1 is positive 4. Good. Okay, looking at this equation, I get a 0 when x equals to negative 3. So let's say that that's right here, negative 3. Negative 3 gives me a 0. And then if I think about values to the right of that, I get positive results. If I put in numbers that are to the right of negative 3, I get positive answers. And if I think of values to the left of that, I'm going to get negative ones, right, where this is the 0. Okay, so now the multiplication of the two, I'm going to get a 0 here, and I'm going to get a 0 here at 3 and negative 3. And then if I pick values that are to the left of negative 3, I'll end up with a positive times a negative, which means that these will be negatives. If I pick values in between here, I'll get a positive times a positive, which means that these will be positives. And if I pick values over here, I'll get a negative times a positive, which will be equal to a negative. And so going back to answer this question, when is this product positive? When is it bigger than or equal to 0? It's going to be bigger than or equal to 0 here. Okay, so then that gives us my domain. My domain is domain equals all the values that are between negative 3 and positive 3, inclusive of the endpoints. Okay, or you can also just say x less than or equal to 3, greater than or equal to negative 3. Same thing. Good, pretty good. finally, last one, we have two considerations. We've got to make sure that the denominator is always positive, greater than or equal to 0, but then also we have to make sure we're not accidentally dividing by 0. So the first consideration means that we have to make sure that t plus 1 is greater than or equal to 0. Which means that if I subtract 1 from both sides, I get that t must be greater than or equal to -1. Good. So that's one consideration. However, the other consideration is that I don't want to divide by 0, so I cannot let t be exactly equal to -1. So I eliminate that extra option. And so my domain is just going to be strictly greater than -1. So domain is t is strictly greater than -1. Right? So we just got rid of this greater than or equal to part. Sure that they have it in a nicer form here. Factor it, set equal to 0. That was the first answer we got. For the other one, same answer we got, from -3 to +3. And finally, same thing for the last one. Must be strictly greater than -1, which we can also write this way as -1 to infinity. Okay, so the very last concept in section 1 of chapter 2, quick little thing, is just thinking about the different ways in which we can represent functions, and there's 4 general ways we could do that. So when we want to represent a function, express what a function is, a relationship between input and output variables, we can do that verbally through a sentence, right? Double the input plus 5, or the square root of the input minus 4, those kinds of verbal descriptions. We can do it algebraically, most popular way of doing it, some sort of an equation, 3x plus 5 or something. Visually with a graph, right? So a graph is a representation of a set of ordered pairs, typically an infinite set of ordered pairs. And we're looking for a pattern that's sort of established by the graph. And there's some classic graphs, some typical graphs that we work with quite a bit. Or numerically with some sort of a table, either a very finite number of values. Either the function is only defined for a finite number of values, or the table provides pattern that we can use to find other values, right? If we can see from a table that we're always doubling the input, we can see that the pattern exists and use it. So see, a single function can be represented 4 ways. Okay, so some examples. So verbally, right? So here's an example verbally. To convert the Celsius to Fahrenheit, multiply the Celsius temperature by 9/5 and then add 32. Right? So it's a verbal description of the relationship between Celsius and Fahrenheit. Okay. Algebraic formulas, right? So here's a classic formula for the area of a circle. So written in function notation, a of r equals to pi r squared. So pi r squared is a very famous algebraic expression. We can also describe things graphically. So here looks like it's a seismograph for earthquakes, right? So we can see visually what was happening at various time points. And in some cases, each one of these representations of a function has its own benefits, and in some cases the graphical method is clearly the only way to really represent information, or the best way to represent information. Okay, and then with a table. So here is a table of values. Looks like this is weight, 0 to 1 in ounces, 1 to 2 in ounces, and then dollars. So this is the cost of mailing a first-class envelope. So 98 cents as long as it weighs less than or equal to 1 ounce. If it's greater than 1 but less than or equal to 2, $1.19, and so on and so forth. Good. So here's another representation of a relationship between two variables. Any questions? Fairly easy, right? This chapter is going to be really easy. We're going to fly through the first few sections, I think. Good. Okay, so practicing. Let's practice with the relationship between Fahrenheit and Celsius. So we had the verbal description. We saw over here that the verbal description was to convert a Celsius from Fahrenheit, multiply the Celsius temperature by 9/5, then add 32. Okay, so we want to describe that in 4 ways. So algebraically, numerically, using a table of values, and then visually using a graph. So if we have Fahrenheit described as F of C, where C is the Celsius value, well, we're supposed to multiply the input value by 9/5 Celsius, and then add 32. To convert from Celsius to Fahrenheit, so starting at Celsius and leading to Fahrenheit, multiply the Celsius by 9/5. Okay, good. So we have a algebraic formula. Right, easy. Numerically using a table of values. Okay, so again, we can just sort of establish a table like this where we have an input value of C and an output value of F of C. And then we can just choose different results here. Why don't we start off with a super easy one? Why not 0? 0 is always good. And let's put these values here. 9/5 plus 32 means we only get 32 there. Let's pick another one. How about another convenient one would be something that's a multiple of 5, right? I could choose 1 or 2 or 3, but then I would end up with a fraction here, and then I'd have to add 32 plus a fraction, common denominator, right? So it's a lot of work. Why not choose something convenient that will result in something I can easily do? So if I let C equal to 5, 5 over here, then I end up with 9/5 times 5 plus 32. So that's going to cancel out to give me 9. 9 plus 32 gives me 41. Okay, and you get the point. So we just keep going. We can come up with a table. Good. And then visually, using the graph. Okay, so we just graph this guy here. We can tell it's a linear equation where the slope is equal to 9/5, and 32 indicates for us what the y-intercept is going to be. So F of C equals to 9/5 C plus 32 means that this part is the slope, and from here, not the 32 is the y-intercept, but 0, 32 is the y-intercept. So if we wanted to do like a rough sketch of this, we know we could do it in the following way. It doesn't have to be a perfect graph and doing it by hand. You just have to kind of identify some of the key things, that's all. So here is a rectangular grid. We know that the m, the slope, is going to be equal to 9/5, and we know that the y-intercept. Okay, so we have a point here, 0, 32. You just put it there and label it. 0, 32. And then I can use the slope, having a value of 9/5, to use this as my rise, and this guy as my run. Remember, slope is rise over run. So I can create a little triangle here where I know this is going to go 5 units this way, and I know this is going to go 9 units this way. And it's not really up to scale because according to my graph, the distance from here to here is 32 units, but then this distance is 9 units. So it's not quite up to scale, but that's okay. As long as we label ordered pairs, then people will be able to follow what's going on. Okay, so we should arrive at another point on the line, and then we can connect them. Good. And so let's label it. If you're going to do this, it's important to label points because it's not really up to scale, and I'm just kind of sketching it. So you need to label your points. Okay, so we started at x equals to 0, and we traveled 5 units this way. So I know that this ordered pair is going to be start off with a 5, and then from in the vertical direction, we started out with a height of 32, and we went up an additional 9 units, so we get to 5, 41. And so there you go. We have 2 ordered pairs. We have a line. We're pretty good. Maybe label the actual line. Maybe label the axes. So this is a case where this is the C value for Celsius, and then out here is the F. Right? So the C axes, instead of X axes, we can use the C axes, the F axes. And then this equation right here is f of c equals to 9/5 x plus 32. Okay, so this is what the author did as well. Wrote down the equation in this format, same as what we did. A little table of values. They chose different ones. I chose 0, 5, right? Looks like the author went by multiples of 10. That's fine. Another good choice, since 5 goes into 10, and we get some easy evaluations there, right? Like for example, for this one, we would have f of 20 is equal to 9/5 times 20 plus 32. 5 goes into 20 4 times. You get 4 times 9 gives you 36 plus 32, which gives you 68. And that's how they got the 68. And then the graph. Good. So they didn't label the ordered pairs, but they labeled the vertical and horizontal axes. Hopefully good enough to be able to tell that 10 traces to 50, right? So that's the drawback of graphs, that they don't give you very precise answers, right? If you're just looking at this graph, if nothing else was given to you, it's kind of hard to tell 20 leads to, you know, somewhere over there, and it's kind of hard to tell exactly where it is. So graphs, you lose precision when you use a graph, but you gain perspective, right? Sort of a global perspective of the pattern that happens at large. So there's a lot of value to graphs.